So, the reaction we just witnessed was combustion. And combustion is something you should be able to identify. We've done it many different ways. We started in redox in our September, came together from the summer. We started in redox because most reactions are reduction, oxidation reactions. And the classic one is combustion. You guys did combustion analysis questions, right? So you should understand with combustion, we're going to start with a carbon-based fuel, usually, okay? So in this case, our carbon-based fuel is ethanol, C2H5OH. And of course, the other reactant in combustion, oxygen. That's not dark enough for me, okay? So oxygen is going to do what to the fuel? It's kind of in the word. Oxidize. And oxidation is actually an oxidizing agent. Make sure you get these words down. It's an oxidizer. It's going to help pull what? Electrons from the ethanol. However, I do want to make the point, oxidation and reduction is occurring. The alcohol is going to lose get oxidized, and the oxygen is going to get reduced. It's the oxidizing agent, the oxidizer. However, when we're dealing with organic chemistry, it's a little bit subtle than metal, non-metal. We had copper and oxygen with heat. We noticed that in our lab we had copper oxide occurring. There was a full exchange of electrons from the metal to the oxygen. So part of your copper iodine, they had to be copper oxide in the flask. Okay? Can't help it because oxygen is everywhere in our environment. Good thing, right? We need that for cellular respiration. However, okay, when it's a metal, non-metal scenario, metals lose their electrons very easily. Carbon is a non-metal. It's over here, right? It's a small little atom, so it likes to gain electrons. It holds on to electrons much more tightly than a metal does. So the oxidation's a little more subtle, but I want to introduce this. But let's go back to the what? The products. We have what? Carbon dioxide is a product. You should be aware of this. When you say combustion, CO2. And what else is a product? And why am I color coding this? Because when you did combustion analysis, didn't all the carbon come from the fuel? And didn't all the hydrogens also come from the fuel? We couldn't work with the oxygen because it was in excess. We found the mass of this using percent by mass, found the mass of the hydrogen, the missing mass was the oxygen. All this stuff is interrelated. I want to fight for you to understand this. It's not just separate little topics. Now, let me talk about what's really happening here because it's really interesting and something you should be able to understand and see because it's something we're doing right now. So if I take this carbon-based fuel, okay, and I don't think I need my goggles to write on the board anymore. So if I take my carbon, there's two carbons bonded together, and it's bonded with the H's. It's an organic compound. Then there's a hydroxyl group, OH. Then I have my O2, which we should know it's double bonded. And then let's talk about Lewis dot diagrams for a second that we did this summer or you did last year. Carbon has how many valence electrons?
6.
Or 4. Okay. That's all good. And this one has 4 as well. Hydrogen has how many valence electrons? 1. So there's our bond, a pair of electrons. By the way, this is being shared because hydrogen and carbon are small atoms. They have a great attraction for electrons. So these two guys are going to share electrons to make a bond. In the salts that we've been talking about, we had a loss and gain of electrons become what? Negatives and positives. Okay, I want you to see big picture. Now, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Hydrogen has 1. So the dashes represent bonds, pairs of electrons. Notice there's a single bond between the carbon. Everyone is following the octet rule. Oxygen, real fast. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Notice the double bond. Okay? Now, why am I drawing this? Because I want you to see the oxidation. Now, The carbon to hydrogen bond, these pairs of electrons are equidistant almost from the carbon to the hydrogen nucleus. Because hydrogen small and carbon is a little bigger, they actually have very similar attraction for electrons. How can that be? Carbon's got 6 protons, hydrogen has 1. Well, because of carbon's other electrons that are in between its outermost electron, they shield for that outermost. So the electrons that are the valence electrons of carbon feel the nucleus about as much as the single electron feels the individual proton. Okay? I just kicked some water I had there for that demo. All right? And we'll talk about that at a later date. But we do know that hydrogen and carbon have about the same attractions. So these pairs of electrons are shared equally between. Guess what? They have a lot of mobility. They're high energy electrons. Now, when this gets oxidized, it really doesn't lose electrons, really, completely, but it sort of does. The most oxidized form of carbon is CO2. So after combustion, a redox reaction, you have the most oxidized form. Okay, what we have is we have carbon, we have oxygen. Look at here. Oxygen, I know, is right next to oxygen. Carbon is right next to oxygen, our periodic table that I'm pointing to. But really, it's so much more electronegative, or it attracts electrons so much more. Okay, it's the reason why metals rust. It's the reason why if you had sushi and you see tuna, if it's sitting out, it's going to go from that red to the gray. Okay, it's the reason why your deck has a nice wood color. Over time, it goes gray. Oxygen is doing that. It's so much more pulling on electrons than carbon. What it does is, now, if we do the, carbon has 4 valence, right? 1, 2, 3, 4. Oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What's the difference in my drawing? I mean, you may say, Mr. Grotsky, carbon is still sharing 8. Sure. Everyone's got the octet rule, but what happened to those electrons? They're pulled closer to the what? So carbon, what? Sort of gets oxidized by the electrons being pulled farther away. That's how we do it in organic chemistry. With metals, it's a loss. But here, it's being pulled farther away. And of course, water, okay, we have what? Same kind of thing happens to here. Water's electrons are where? Pulled closer. And that's why water is polar. Where's most of the electron density in water? By the oxygen end. Where is there not a lot of electron density? So that tells a big story what's going on here. So any case, this is oxidation. You must know what combustion is. Now, it's an example of redox. But let's get back to what we're after today, which is limiting reagent. I just did a reaction where we burned methanol and oxygen. You saw it go down the tube. And you saw it go down the tube. And when you saw it go to the left, it was moving, as you guys said, to get more what? Alcohol. Alcohol limited the reaction. Once it ran out of the alcohol, the reaction stopped. Limiting reagent is the reactant side, that runs out first. And when it runs out, the reaction stops. And these are usually reactions that are completion reactions. Completion reactions meaning that there really is no equilibrium. They go one way till they stop. Okay, so it's important we get that. So we visually saw the limiting reagent in the reaction, but now if you're given a certain measure of the reactants, we have to calculate who limits the reaction. It's very important. So the first step, based upon what we learned from Prost and Antoine Lavoisier, we have to balance our reactions. Because of the what? Law of conservation of mass by Antoine Lavoisier, we can balance this. Because compounds have a definite proportion, we know that these don't change. So let's go balance this, because we're going to need to do stoichiometry. All right, so I got 2 carbons, 1 carbon. All the carbons from the ethanol have to become CO2, so I throw a what there? 2. Okay. I have, don't forget this one here, I have 6 hydrogens. How do I get 6 hydrogens over here? All the what? You learned this already. All the hydrogens in combustion analysis, like you're going to see in a test question eventually, okay, come from the H's in the water. Everything's interconnected. Now, our oxygens aren't balanced. 2 times 2, I have 4. And then 3, I have 7 oxygen atoms on this side. Right now, I have 3. But I know this guy, I don't want to change this guy, right? Because there's 2 H's and 6 H's, so I'm going to leave that alone. So this takes 1. I need 6 oxygens here. How can I make 6 oxygens? Put a 3. Notice when I balanced, I did not change the chemical formulas. The chemical formulas are determined by our labs that we've been doing. You don't just arbitrarily. We found those. So my friends, that is the ratio we need. These ratios, what does it tell me now? For every 3 of these O2 particles, molecules, I need 1 of these to make 2 of these to 3 of these. And we're going to do stoichiometry to figure this out. So, loaded with that, and here's the question. Now again, this is the demo. We knew visually what was limiting reaction. We ran out of our fuel. And we had O2 outside of it, and of course it didn't go burn us all to a place where you go for your bed. Okay? Don't want to say hell on video. But the point is, that didn't happen. So here's the problem. I have a gram of this reactant, and I have a gram of this. Who's the limiting reagent? Well, to do this problem, we need stoichiometry. And we've done this already, but we haven't looked at it this way. At this point in your careers, you've taken how much of a starting reactant and figured out how much product you should make. Hey, in your copper iodine lab, you knew exactly, pretending this is copper, how much copper atoms reacted, and then you calculated how much product you should have made based upon that. We've done that, but now we're going to do it a little differently. Given the starting amounts of both of these, I'm going to figure out how much of the other one I need. So to make my point clear, okay, I'm just going to do this. Given, so here's the problem. I have a gram of the ethanol, I have a gram of the oxygen. Which one limits the reaction? To answer this question, I'm going to solve for how much of the other one I need to make this disappear. So if I've got a gram of C2H5OH, C2H5, okay, so I said it, of ethanol, easy to say that, how many grams of oxygen do I need to make all of this disappear? And that'll tell me who limits. Let's go do that. All right, so first step is that I have a gram of C2H5OH, and I'm going to choose a color that I think might be blue, but who knows. First step, because I'm going to do stoichiometry, I'm going to use these ratios. I can't be in ratios of mass, I have to be ratios of how many, mole concept. So I'm going to convert to moles. So grams go in the bottom, 1 mole. Of course, we're cool. We don't say the E when we say mole. All right. Now I need to know the conversion of a mole of ethanol to grams. Well, party people, that's the molecular mass or formula mass. Add up all the atomic masses. So I have 2 carbons. Each atomic mass of carbon is 12. Good. 24. You're going to know a lot by heart by doing this eventually. You have 6 hydrogens altogether. And because each one has a relative atomic mass of 1 for hydrogen, why? Because it was the lightest gas. Remember, we found the atomic masses by comparing the gases. It's 1. Now, I'm rounding off to whole numbers. Some people, when they do these problems, they want to use a certain, they want to use more precision to the hundredths place. I'm going to have you round off because we're after the concept here. You're good rounding. You really are. Some people would disagree with that, but you're good rounding. Okay? This is really about the concept. If you're going to do this, okay, to get a more precise answer, you would use those decimal places. Okay? Any case, and of course I have 1 oxygen, 1 times 16. Okay, add these together, I think it's 46 grams per mole. That's my unit. And that's my converting factor, party people, 46. Okay, that's something we should have down. Okay, so that's going to look, now guess, grams go bye-bye. Right now this tells me moles. Good, I'm in a how many number. That's why we need moles. Now here comes the stoichiometry. What am I trying to do? I'm trying to relate the number of particles of this eventually to grams of this. But I know it's a 1 to 3, so the moles are 3 times as great. So I'm just going to keep myself organized. I'm going to get rid of C2H5OH, and I'm going to get O2. And there's where my stoichiometry appears. This is just a conversion. This is where my stoichiometry appears. I'm going to use ratios. Remember electrolytic compounds or electrolytic electrochemical cells? We were able to relate how much copper, let's say, was collected at the cathode By knowing the number of electrons and the ratio of electrons in the half reaction. That was stoichiometry. So what's the ratio? There's one of these to 3. So, changing my color to show you how important this is, there's a 1 to 3. Notice what cancels. So now this expression, because I'm using my units, I'm never thinking, when do I multiply or divide? I never think that. I use my units. I have moles of O2. Great. But I want to convert that to grams, because I have grams. So last step, because mole's on top, 1 mole goes in the bottom. And using my mole concept, because we forced a mole to equal the atomic mass, 1 mole of O2 should be 32 grams. Look what cancels. I'm left with grams of O2. Pretty simple, okay? The math isn't that difficult. It's what it means is everything, okay? So do the math with those that, how do I attack this? 1 divided by 46 times 3 times 32. And when you put that in your later of calcs, just make sure I get the right answer too, I get approximately 2.09 grams of O2. So, party people, that's how much I need. What does that mean? That means I need, what? 2.09 grams of O2 to make 1.00 grams of what? C2H5OH disappear or completely react. Completely react. That's what I need. I need 2.9 grams of O2. What do I have?
1.
Do I have enough oxygen to drive away my ethanol completely if I'm starting with a gram of each?
No.
So I do not have, enough oxygen to drive away completely. So that means that this doesn't completely react, does it? So that screams to me that that's the excess chemical. Who is limiting? Oxygen. Now, if you don't see it, we'll do the second one together, because sometimes you need both. But honestly, if you do one Stoich problem, you should already say that, hey, excess chemical must be the ethanol. Why? I don't have enough of the oxygen to make it all disappear, so therefore a lot of it's going to stay unreacted. If you can see that, great. If you don't, let's do the second one just to reinforce. Both of them will give us the same answer, just a different way to do it. So let's do this one. Start with 1 gram of O2. I want to go to moles, because I have to be in a how many number, okay? And of course, a mole of O2 is 32 grams because it's 2 times 16. And I want to get rid of, grams go bye-bye. And now here comes a stoichiometry. I want to get rid of O2. It goes in the bottom because this is over 1. And I want to get my ethanol, C2, C5OH. What's the ratio? There is 3 O2s to 1. Where am I getting that? From my balanced chemical equation based on law of conservation of mass. There is no law of conservation of mass. If there's no law of definite proportions, none of this can be done. This is where chemistry began. Once we had a mole concept and an atomic, what? Or had a theory of atoms and particles, this is where we could do what? Predict how much of one to the other. So this is so important. Okay, this is where made chemistry became a science. I'm going to go back to grams. Oops. So I do that. Notice what cancels here, O2. So this expression right here is moles of ethanol. Let's go to grams. Moles on top, right? So I put a mole in the bottom. I already know the molecular mass. 46, right? Okay, so this is 46. Let's check to make sure everything cancels. I want grams of ethanol. There it is. Put this in my calculator. 1 divide by 32, divide by 3, times 46. Okay? You put this in your later of calc. Okay? And you get approximately, guys, make sure I do this right, 0.479 grams of what? C2H5OH. And what does this mean? This is how many grams of ethanol I need to make a gram of O2 completely run out and totally react and stop the reaction. Do I have, remember, look at the need. Do I have enough ethanol to drive a gram of O2 away? Yes. So clearly, don't I have more than enough? If I was to ask you how much excess, could you calculate it? You subtract 1 from this. So both of these Stoich problems, where you did what? Figured out how much of the other you need, clearly scream, okay, that this one is the excess, and this one was limiting. You say, well, why do we care? Because in an AP problem, here's what they'll do. Given a gram of ethanol, a gram of O2, okay, how much CO2 do we make? Oh, it's easy, just pick one. Don't pick one. What if you pick a gram of C2H4? What if you pick a gram of this? Aren't you going to overestimate how much actually reacts? You got to go find who's the limiting first. Then start with that one, okay? So it's important. Now, if you didn't like that, okay, and again, I like doing need and want, so if you notice, we have, this is what we needed. This is what we have, and that clearly is an easy one to see. We need this much. We have more than enough. Therefore, C2H5OH was excess. Okay, and you can look at it from the other way. But if you like doing this, and you're fine with this, and you can see it, some people say it's a lot of moving parts, and sometimes we're doing a lot more work than we have to. What is this really about? Moles to moles, right? Now we started in grams, so I went back out in grams. You guys did a molarity worksheet this week where you started in milliliters and you went back out to milliliters. Okay? So if you had this type of problem, I'm going to show you a little shortcut method that I think really will help you in terms of speed and efficiency for these types of problems when you don't have a lot of time. Okay, case in point AP. So I call the chart or stoichiometry method. Okay, and people teach this. It's not something I created, but it's definitely something that does help you go through these questions a lot easier. So the Stoich table, if it's stoichiometry, what's essentially stoichiometry? Using the what?
Molar ratios.
The ratios of how many particles, mole ratios, whether it's electrons or not. That's what this is. We can't do chemistry unless we deal with these ratios. You got to have atoms and particles, and you have to have a mole concept. So, in this Stoich table, party people, you must, Christmas, not that, you must be in moles. Moles are exclusive. Can't get in the club unless you have moles. Let's see, you want to join the club? Let me see, show me moles. Oh yeah, you got to look at it. Stop. Sorry. But if they don't have hair, then they're what, beauty marks? I don't get that. All right, so in any case, they're beautiful. Oh, they're grown as a mole. All right, now, this is called an ice table. Okay? I don't know if you're aware of the, dun, 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 dun. Stop, collaborate, and listen. Okay, yeah, Vanilla Ice. But the point is, and you ripped that song off, I think, from Queen, but the point is, the beat, I guess. Ice table's initial change in N. So this is going to help. So we're going to start with moles. So clearly, all I need, party people, is this point right here. I need this information. So let's go get moles. Let's put that in. So when we take 1 divided by 46 for the methanol, okay, and you put that into your later of calcs, I believe you get, and you can check for me, because I do make mistakes, I am told. Okay. I get the mole from 1 divided by 46, 1 divided by 46, right? Just getting the moles in here. Stoichiometry is based on moles. I get 0.022. Everyone agree? Okay. Now do the same for the oxygen. Different number of moles, right? Because it's a different molecular mass. 1 divided by 32. And when you do that into your later calc, I believe you get 0.031. Okay. I don't need the rest of that. Now we're going to move to this. This is where I think life gets easy for us. Okay. Now I know it's a 1-to-3 ratio. That I get from balancing. That is everything. Without those ratios, this can't be done. So watch how I decide who is excess in the limiting reagent. First, let's start with the ethanol. Okay, change colors because I can. All right? So if this guy, in order for all of this to react, okay, how much of the O2 do I need? Can everyone clearly see I'm going to need 3 times the number of particles for all of this to react? It's a 3 to 1. Isn't mole a number of kind of particles? Isn't it like an abbreviation? So what's 3 times 0.002?
0.066.
So we take take this times 3. And what you get is what? 0.066, right? So what I'm saying is take this and times it by 3. In order for all of this to react, I need to have at least 0.066. Do I have enough? No. So I don't have enough of this to make all this react. Excess chemical. Cool. Now, let's do it in the opposite, because we want to finish the chart. Change colors because I can. Now, how about this way? In order to go from here to here, it's what? Divide by 3. So take 0.03 and divide by 3.
0.01.
Yeah. All right, what's a third of 0.03? 0.01, right? So wait a minute. In order for all of this to react, I need to at least have 0.01 of this. Do I have enough? Yeah. So how much is this going to go bye-bye with? If all of this is going to react, isn't 0.01 of this needed? So I write that there. That's only I'm going to use of that. Why? I'm only using 0.01 of this. Because that's all this what? Needs, right, to go forward. So, how much am I going to lose of the O2? 3 times that much? All of it. We figured out all of it's going to go. So what do I put there? Yeah, 0.031. The limiting reagent is always going to go to what at the end? 0. It's going to run out. So the change is what? Negative, negative. Why are these changes negatives? I'm starting with reactants. As I drive it forward, they're going what? And the limiting reagent stops the reaction because you run out of it first. So the limiting reagent always goes to what? And that screams limiting reagent. Now, I could ask you how much excess. Only that much is needed to make all this disappear. We didn't have enough of this to disappear, so how much is left? Subtract that. 0.012. And that's the what? Excess. Okay. So you tell me which one you'd rather do. Except you have to remember, you're always dealing with what? Right, now, here comes the question. How many grams of CO2 are produced? If you didn't do a limiting reagent problem, if you didn't do the box method, you may take a gram of this and do a Stoich problem like you did in your lab. But you would be overestimating the CO2, wouldn't you? Okay, so let's pretend I don't have the box question. I would take, once I figured out who's limiting reagent here? Oxygen for both methods. So if I start with what? Grams, so 1 gram of O2. Get rid of the grams, go to moles. This is 32 grams, right? Here comes a stoichiometry, get rid of O2. What am I looking for? CO2, what's the ratio? Look at your reaction. 3 to 2, right. So there's, my short-term memory's gone to psych. So there's 3 O2s to 2 what? Notice I put CO2 on top. Keep myself organized, easy. Now I have moles of CO2, but I want grams, right? I have 1 mole. Molecular mass of CO2, if we went to the molecular mass party, it's actually 44 grams. Okay. Molecular mass of water, anyone know? 18. Gotta go to those parties, guys. Okay. How about glucose? 180? Oh, we'll get there. It's still early. So this is 44 grams. Let's do the math. Okay, when you do the math, I think, who's got it? Yeah, 44 grams per mole, because you have 12 plus 16 plus 16. 0.917? I think you're right. Now, could I do another way? Hey, couldn't I take 0.03? Now, another way is, couldn't I start this another way? Couldn't I take exactly how much this actually reacted and convert that to CO2? That would work too. I can't use this. That would overestimate my answer. Or, how about if I use my chart?
You could just use them.
Yeah, I could either use the 0.03 moles of O2 and do a Stoich problem to grams of CO2, or I could start with what? 0.01 moles of the ethanol. As long as I'm using exactly what reacted, the easiest thing is to always use your limiting reagent. Whatever limiting reagent you have, just stay with that. That's exactly what you're going to use to identify the others. I don't care which way you do, but I'm telling you, if you're trying to find a limiting reagent, think about your homework 2 nights ago with the milliliters. Remember all those steps from milliliters to milliliters and using molarity as a converting table? And you better be doing your homework, guys. Wouldn't it be easy to go find the moles, do the ratio to the moles, and just eliminate the milliliters part? So that's why that's faster. Now I wanted to show you how to make those conversions. Question, Tristan. Tristan.
Alright, so is it always the limiting reagent we use to find the grams of CO2?
Yes, that'll always work. Could you use the other? As long as you know how much of it reacted. Don't use the total excess. So generally speaking, use your limiting reagent. You'll never get it wrong once you identify it correctly. How much of it? Because it's going to stop. Okay, your homework is the back side. It's connected to this. But I have a couple other concepts, unfortunately, tied to it. You'll need the, what? The video to walk you through it. Okay? See how it's all fit together. See you tomorrow.